So let's look at this problem. Again, we're trying to, this is a beam that's simple supported here, and I believe at B that's a pin connection. Okay, so it looks like it might be a fix, but it's not. So we'll say B is a pin and A is a roller. Now it supports a uniform dead load of 500 newtons per meter, a single concentrated load of 3 kilonewtons, and we want to first determine the maximum positive moment at C and the maximum positive shear at C. I'll do shear first. We just did a moment one. I'll do that one just to get us started. So let's see if we can use Mueller-Breslau and get this. So I'm going to look at the shear at C, and I'm going to go ahead and extend down some lines to show the beginning and end of the beam, and I do want to know it at C, so I'll draw a line there. Now remember what we do at Mueller-Breslau is, what do? We come up here and we assume we have this very interesting shearless connector device, right? And we put positive shear on one side and positive shear on the other side. So looking at this left side, how is it going to move? Is that edge of the beam at C going to move up or down? Down. So I'll say it goes down here. And we'll have a shape that looks something like that. What's going to happen on this other side? Up or down? Up. These slopes are the same. Okay? So now we got some calculation to do here in our head. This is 1 meter, and this is 3 meters. So I know that this height is to 1 as this height is to 3. Well, you can just clearly see that this value is going to be 3 times bigger than this value. Right? Yeah. So 3 times x plus x is 4x, and that has to be 1, so x is 1/4. So this is going to be minus 1/4, and this is going to be 3/4. It's 3 times bigger, and it adds up to 1. Do I need to write that down? Is that okay? Can you guys see that? Mr. Curry, you're looking at me very strangely.
Can you write it down?
Are you still thinking about the lightning guy, or you moved on? Get that out of your memory. So let's do it this way. Let's just say this is H, right? And we know by similar triangles that this has to be 3H, right? Why do I have to know? Why do I know it's going to be 3H? Well, H is to 1 as what is to 3. They have to be equal, so this would have to be 3H. And then, of course, you add those two together, you get 4H, and that has to be equal to 1, so H is 4. That's another way to look at it. I'm done. Well, I'm done with drawing influence line. What's the problem ask me for?
Maximum positive shear.
So where would the positive shear be? Well, I'm going to work with this positive side of the graph, right? So if we first start with the, what did they give me first? A uniform dead load. Okay, so we'll start with, just because it comes first, I'll do that. So I've got a dead load, and it's uniform. So I have to apply the uniform load over the entire structure. So I'll need the total area under this curve, and the value of the dead load is 500 newtons per meter. I'm going to change that to half. So that would be a value of 0.5 kilonewtons per meter times the area of this graph. So they're both triangles, so I'll have the 1/2 base times height. So for the first one, the base is 1 meter. And what's the height? Negative 1/4 meter. In the second one, I've got a base of 3 meters and a height of 3/4 meters.
Are those like a 1/4 and 3/4? Those are units, right?
No, these are meters. Oh, this is shear. Sorry, there are no meters. I was doing moment in my head. Sorry. Yeah, these are not meters. These are dimensionless. Because that's a shear.
Every moment.
Did you say moment? Yeah, I thought I heard somebody saying that, so I threw it in there. Yeah, it should just come out with the unit of kilonewton. So the kilonewton per meter and all this will just be meter.
What are we determining, the maximum positive moment or the maximum positive shear?
We're doing I'm doing the shear first. This is an influence line for shear at C, so I'm doing part B first. I thought it would be the easiest one to do first. So far it has been, except for the error in the unit. So I don't know what that would be. Somebody's going to have to help me with that. 2, 4. I say the answer is 2, but I'm guessing. What'd you guys get?
I got 0.5.
You got 0.5?
I got 1 half.
You got what, 100?
1 half.
1 half. Oh, right, 0.5 twice. That seems like a good sign. Anybody else?
I got 0.5.
0.5? So that'll be 0.5 kilonewton. All right, so next we'll do, we don't have a uniform live load, we just have a dead load and a concentrated load. So the only live thing I have on this problem is a concentrated load. And we're trying to find the maximum positive shear, so where do I put that? Where's the positive ordinate on the graph? Just to the right of C. So I'll have my 3 kilonewton force times the ordinate, which is 3/4. And that should give me a value of 9/4, which is what? 2.25. So you add those two together and you get the maximum positive shear at C will be those two added together, which is what? 2.75. Okay? So now we're going to switch and go back to part A, which is the maximum moment at C. Same spot, but now we want the moment. So let's draw a little quick template for our influence line, but now we're looking for the moment at C. This will have units on the ordinate of meter. Right, Mr. Tyler?
Yep.
So there's the end of the beam. There is point C. So remember, we're going to go back up here now. We're going to put our hinge here and apply positive moment. So that point will move up or down? Up. So I'll just pick a value here. It'll swing back to A, and then this will hinge over and swing back to B. So I just need this value right here, which corresponds to my unit load being right over D. So I'll come here and I'll draw my beam, and I will assume that I have a reaction AY acting up, a reaction BY acting up, and I want my unit load to be right here at C. So when you're at C, that's 1 meter, and this would be 3 meters. Now I want to also cut it at C and find the internal moment, so you can decide now whether you work the left side or the right side. Yeah, no apparent reason. I'll work the left side. So first I'm going to find the reaction at A. I can find my reaction at A by summing moments at B. Make sure it's in equilibrium. So summing moments about B, what's the moment due to my uniform load?
Positive.
Yeah, it's a positive moment of 1 times a moment arm of 3 meters. And AY reacts with a negative moment with a moment arm of 4 meters. So it looks like AY is 3/4. So now if I cut the structure, I'm cutting it here looking at the left side. So AY is 3/4. We just found that. And I'm looking for the internal moment at C, and that's 1 meter away. So I can sum moments again at the cut, make sure it's equal to 0, and what do I get? I get the internal moment, which is positive, and this reaction is going to create a negative moment. So it looks like the moment at C is equal to 3/4. And that's weird, it's going to have units of 3/4 meters. So this becomes, oddly enough, 3/4, just like that. Are they related? No, just coincidence with the values. Now I need to redo this part using this graph. I may be able to squeeze it in here. So let's do, I'll use a little notation. I'll say dead uniform load, dull. All right, so it's going to have a value of 0.5 kilonewtons per meter times the area of the graph, which is one triangle. So it'll be 1/2 base, which is 4 meters, times height, which is 3/4 of a meter. What's that equal to? 0.75?
0.75.
So that's 0.75, and that'll have the units of kilonewton meter. And then we'll do a live concentrated load. That's 3 kilonewtons. And then what value do we choose? What ordinate value do we choose? The largest. 3/4. And that, interestingly, is the same numerical value. But it's kilonewton meters. So the maximum moment at C will be these two things added together, which is 3. How do you like that one? So a simpler diagram than the previous one, but asked you for two different things, right? Shear and moment. The other one was a little bit harder, just asked you for moment. So either one of those types of problems are valid for the exam. Other questions? All right.